In previous videos of this series, we encountered the slogan that monads axiomatize algebraic structures. We've seen monoids and or lists as examples of algebraic structure. And then we've seen that the monoids and lists support four operations, which we called map, iter, mu, and lift. And these operations satisfy certain equations, which I asked you to explore in a previous exercise. So this video is about the next exercise, and here we're doing it the other way around. So I give you the equations, you can think of them as a specification, and I ask you to implement the operations map, iter, mu, and lift. And our example is the simplest monad that is interesting, I would say, and that's the arrow monad. So if you look at line number 4 here, I call it wrap because it wraps a data type A into either an arrow or a value. Let me just quickly write this down in more mathematical notation. So we can think of wrap as an operation which takes a set x and returns a set 1 plus x. So this needs a little bit of explanation. So the plus is disjoint union, and 1 is just an abbreviation for a set that has just one element. Is an abbreviation for a one-element set. And so then, what about arrow and value? So a nice way to think about arrow and value in line 4 is to think about them as maps. So as maps which are injecting or including the 1 into 1 plus x, and the map which is including the x into 1 plus x. So what appears as so-called constructors in the Haskell code, arrow and value, we can think of these as functions which are including a type into the disjoint union, or a set into the disjoint union. Okay, so now let's come to the four functions: map, iter, mu, and lift. So if you look at the code, then you will see that the definition of iter, mu, lift, and map they're not all correct definitions, right? So like if I load the file, and then if you scroll down, there's a function which is called test all. So if you run test all here, you will see that some tests return false and some tests return true. So the task is to implement the four functions in such a way that all tests return true, and essentially map, iter, and lift, right? So they look at the moment they just return error. So this is not the correct definition. Okay, before I leave you to do this, maybe just a few more words about the definition of mu. So we will see later that all the algebraic equations, in a sense, are kind of encoded in the mu. So maybe remember that when we talked about automata, right? So we said that every letter can be considered as a function on the states, but letters are not closed under composition, right? So we had to turn letters into words in order to close the functions under composition. And something similar happens here. So what the mu is really all about is that what happens if we iterate this type constructor, right? So what happens if we apply it twice, and then the question is, can we flatten or reduce the values in rep x to values of rep x? And if you think about the application we have in mind here, error handling, so what happens if you get an error? The function returns an error, and then another function continues computing, right? So then this function still has to return an error. The error has to be kind of passed upwards through all the recursive calls. So this gives us the equation that value of error equals error. And then we want that the value of a value is just the value. So the implementation of mu should be correct, and the exercise is to implement the other 4 functions. Thanks for watching.